Looks like it's recording just fine. Thanks, Grant.
Okay, cool. Yeah, so just kind of continuing a little bit from last time and then also doing some new stuff. So I think all these things are good. And also I just wanted to say at the start, thanks for letting me do this. This is super fun for me. So I hope you all enjoy it as well. Really appreciate it. Okay, so first things first, just kind of going through a couple sort of loose ends from last time. So Sally's not here right now, but he just said something about he wondered what the lost landscape would look like for a transformer, like our new architectures. And I just gave it a quick Google. I didn't do much research, but I think this right here is one like vision architecture that uses a transformer. And I think here's the paper, but I think it's saying that this is much flatter than the typical ResNet. So I think what he was, just guessing at, I think it might be true, and it seems like some people at least are paying attention to it. Um, and then low dimensional trajectories. I thought that Jerry may have been wondering about this, or maybe everyone was. I can't remember, but I just gave it a little thought, and this is my guess at what they're doing. I don't know for sure. I didn't read too much into it, but basically, remember I was saying like in the optimization trajectory, they said it was low dimensional. And my guess is what they're doing is they're taking all of these points in weight space as it optimizes and then doing like a PCA on those and then determining how much of that variation is accomplished by, or captured by just a few of those first dimensions. So I don't know if anyone else has seen anything like that, but that's my guess. And then just in a different image here, let's say each of these points in weight space as you optimize down here, maybe they're just along this line. Kind of something like that. I also, have you previously watched the Yannick video on like the like ensembling? It was like 2 years ago, but they did something about ensembling for like the lost surfaces, and they basically did like 3 initializations here, and then they like optimized into like different directions. And then this is where they all, went to. And I just thought this was kind of a cool picture from sort of a low dimensional trajectory view, but.
Grant, are those different? Are they optimizing for different objectives there?
No, it's the same objective. They just like these little initial differences went to totally different points in weight space. And then, so I think this might be a really cool video if people like it or would be interested. Not me to do. So I know people are doing stuff next week, but basically what I think they found was, they optimize differently and they all, you've probably read the papers where at the different local or mins, they all have about the same performance, right? But what they found in this paper was they all had the same performance, but on completely different parts of the data set, right? So like, let's say this one got the first 10% wrong and the last 90% right. This one got the first 90% right and the last 10% wrong. And so the function that it's converging to is a different function. It just so happens that they perform the same.
Wow.
Which is super counterintuitive to me. And I'm in the middle of watching the video, so I don't have like all the details, but
So is that in support of the idea of ensembles then? Is that where that goes?
I think that's something like that. Yeah. Yeah, I was very surprised too.
Yeah, very interesting.
So
Yeah,
one
go ahead.
comment. Well, if I could, two quick comments.
Please do.
All right. So one is there's a bunch of research, a bunch of papers that are starting to come out where people are looking to see if you train it with different random weights, and you end up with very different weights at the end. Are those final weights just some variation of the same weights, right? So if you just sort of permuted them and you scaled everything down by a factor of 2 on this layer and you scaled everything up by a factor of 4 on that layer, would you just wind up with the same thing? And people have been able to successfully build some kinds of transformations of weights from training set 1 to weights from training set 2. And I think how they've proved that is that you can take like half the weights from training 1, and then the other half the weights you take from training 2, but transformed, and the thing still works. So that proves that that transformation kind of, really did do its job. But the other thing that can happen is, say you're doing classification, and you've got some examples where you look at it and you're like, I don't know. Is that a blueberry muffin or is that a chihuahua? I can't tell,
Yeah.
right? You could get that different performance you were talking about, Grant, by just putting the decision boundary on either side of that set of photos. And so in one case, right, you do slightly better on the chihuahuas. On the other one, you do slightly worse on the blueberry muffins. And but maybe they are somewhat equivalent models. It's just, you know what I mean, this tricky thing you've got on the inside. Yeah, I thought the blueberry muffin chihuahua thing was hilarious because it was like not what you would think off the top of your head. If you said like, what is a model going to have trouble with? It's like I would have never dreamt blueberry muffins and chihuahuas.
Yeah. Yeah, pretty funny. And yeah, so Ted, that's kind of what I would have thought, but this is saying otherwise, I think, which is, and again, I haven't watched the whole or read the whole
Yeah.
thing, but yeah.
Right.
So
No, so
Is this-
these are not necessarily exactly corresponding models with just different permutations, variations of the weights, but they still might be roughly, I don't know what the right word is. They might perform identically on clear examples, and if the ambiguous examples are coin flips, then that's where they might differ. Right? Like I wouldn't expect something where you're like you're doing MNIST and this is like a very clear 8 that like that's the one that it gets wrong compared to the other one. But like
that
just
is
a
what they
weird
said.
one.
That is what they
Yeah.
said. It's not
All right.
like an inherent difficulty. It's literally just getting different ones wrong.
Okay.
I don't know.
Does that speak to the fact that, we're evaluating this with our human biases and senses and things like that, and it's doing something else that, out of our realm of experience, shall we say, to make a comparison between A, B, and C in this, or 0, 1, and 2 in this particular case?
What's that, Jerry?
I think part of it could be that we don't understand why I got it wrong, Jerry. Right?
Yeah.
But
yeah.
but I do think that we have this hypothesis that data lives on a lower dimensional manifold within the space of all, possible inputs, right? So,
But are you saying on one data manifold, Ted, or on different data manifolds?
I don't know if I can say it like super technically accurately, but people are just saying that whatever the problem you pick, MNIST or ImageNet or whatever, there's just many, many, many more possible pixel values than there are coherent images that we can relate to, and that all ImageNet images live on a smaller dimensional manifold, and that theoretically within that manifold you can find the dog region, the cat region, the whatever, right? So I think that's where a lot of people's intuition is, that if something seems to us to be very obviously different, then it should be farther apart on that manifold. I don't know if that's a valid intuition, but I think that's to what Grant's saying. Like if you're surprised it got something that you think is a pretty easy example wrong, then that's where that intuition comes from.
Yeah. Well, I guess that's what I was kind of getting to. It's the intuition part that is incorrect, because it makes an assumption that the model has the same intuition, shall we say? Just a thought.
Yeah, absolutely. Okay, what do you think? Next slide. Keep her going. All right, so and this is still just a little continuation from last time. We talked about slicing in many dimensions, right? Billion dimensional space, whatever it is. And then we just pick random directions, and then we plot them as if they're X and Y, like perpendicular, right? But if they're not perpendicular, that geometry is totally not right, if that makes sense. But what happens in many dimensions, most vectors, if you pick two random ones, they actually are orthogonal. Yeah, so did everyone know that? I did not know that. I was very surprised by that. And so I just kind of, made a little drawing, little back of the envelope calcs, right? So in one dimension, pretty much everything is nearly collinear. And then in two dimension, only 28% are, and then 6% are orthogonal, nearly orthogonal. And then 3D, so this number keeps rising and this number keeps dropping, right? So kind of interesting.
How far up
if you
did you
weren't
take it?
familiar, oh, go ahead, Roger.
Oh, I was just wondering in his calculations at how far, oh, you've got the equation for it down below here.
Well, Yeah, this is just like another kind of argument that I saw online. You know, if you're going to, you know, if you have n dimensions, right, then, you know, without loss of generality, you can just pick one vector here, right?
Mm.
And then if you dot it with, you know, assuming some sort of average right here, the overall dot product is going to be 1 over root n. So as n gets big, yeah.
Yeah, so if we get like in the GPT embedding space of 768 dimensions, everything is orthogonal basically.
Yeah. But I think it's in the weight dimension, not the embedding dimension, right? So it's in the billions.
Any high dimensional space,
Yeah, any
Yeah.
high-dimensional,
really. Yeah.
Yeah.
So Grant, I don't know if you're familiar
Mhm.
with the term curse of dimensionality.
Yes.
Yeah. So that's where you can look up these things and you can see, for example, not only are most things close to orthogonal, but that distance becomes very hard to measure in high dimensional spaces.
I actually have a slide at the end for if we have enough time.
Okay.
So maybe we will do that one. That'd be okay. So yeah, I thought that was kind of cool. And then I also looked a little bit just to kind of go into detail on the method that they were doing. So right here, this is basically approximating what they're doing, right? So I think if I wanted to, shut one of these off. Okay, E. All right, so basically what's happening is, let me turn on the surface. So now we're getting into GeoGebra finally. Okay, so let's say this parabola is our error surface, right? And then your X and Y are basically the weights and the biases. So we're doing it in 2-dimension space, but theirs would be billions, right? And so, you know, in just this illustration, we're going to slice it in one, you know, this one dimension. We're just going to slice along the X, but really it would be picking any random direction, right? So it would be any direction in this X and Y plane, right? And then, so any other random direction is going to be orthogonal. So I said, okay, let's do this as the thing we're seeing, right? So this, if this will go away. Yeah, so this line along this plane is basically the same thing as the air surface that we were seeing, right? That's this thing. And then what we can do though is, the point is, if we're optimizing in that space, we're not actually going along the trajectory that we saw in those air loss landscapes, because the trajectory is orthogonal to basically everything, right? So E, this point here, is basically the trajectory of the actual optimization, right? So as E is going down this path, right, then this F is what we would see from the loss landscape perspective. It would basically just drop down into the bottom and it wouldn't follow the loss landscape at all. Does that make sense? Shulin, I see you shaking your head. I like it. Roger, you look skeptical. You're muted, by the way, Roger. Yeah.
Keep going, don't stop for me.
Okay. But yeah, so I thought it was kind of interesting. So yeah, it does it, that we're seeing the loss landscape just so we can see the shape of things, but that's actually not what we're doing the trajectory along. So like when we did like the gradient descent, like we clicked a point and it did the gradient down it, that's not the trajectory that the optimization is actually following. So kind of interesting there. It just is showing you about gradient descent in general. Okay, so I'm gonna leave that. Okay, so now basically moving on away from stuff we talked about last time to kind of get into new stuff and sort of some other ways to think about loss surfaces, loss landscapes. And then, you know, maybe we probably won't, but like do a little optimization on the end, because once you talk about the air surface, what's the whole point of talking about that is because that's the thing you optimize, right? So you would almost always talk about the air surface in context with optimization. But let's do some function transformations. So does everyone remember, like from pre-calc, their function transformations? Does anyone remember these? The A times F of BX plus C plus D. Does it ring a bell? Thumbs up, thumbs down. I see a no from Ted. No. Roger, maybe a little shaky. Okay. So this this might not seem very important, but I think it's really useful. Okay, so what happens in these function transformations is, so you have a function. So I just made a ReLU, right? So I just started with a ReLU, and I can just draw that with this purple line, right? And so then I made 2 points. So first of all, every function can have 4 transformations, right? So what I did was I plotted 2 points, and I used the x of each of those points as one of the 4 transformations, and I used the y as 2 of the other 4 transformations, right? So B, this point B, when I drag this around, I'm using the x component of this to move in the x direction, and moving in the x direction is this C value here, and the D value is the y component of this B, right? So when I move B around like this, it's moving C and D, and so it's dragging that function around, right? Okay, so now when I move A around, A is those other 2 parameters, right? So when I move A, I took the X value of A and I used that as B, and I took the Y value of A and I used this as this A, right? And so what they are is this one is a vertical stretch. This one is a horizontal compression. This one is a horizontal shift. And this one is a vertical shift, right? So and this helps a lot with the universal approximation theorem, right? So if we can move these functions in every direction we want, and then we add a bunch of them up, what happens is we can approximate any function, right? Good. Okay. So just kind of wanted to show those 4 transformations on the ReLU, because that's exactly what a neural network is doing. Yeah, I see Sheila shaking her head. Okay, so what it means is this right here is the input. So this is the initial X, right? And then B is this number, C is this number, right? So this weight right here is a horizontal compression. And then this weight is a horizontal shift. And then once you wrap this in a ReLU, and now you're applying another weight that you're multiplying over here. And so that's a vertical stretch. And then D, that bias term, is a vertical shift up or down. So these 4 movements that we're doing right here, like this, these are precisely the 4 movements that happen inside a neural network.
Specifically a 2-layer.
Specifically a 2-layer.
Yeah.
And so now when you compose more on, you're just doing the same thing over and over again.
So 2-layer
But-
with only 1 neuron in each layer. You add
Yeah.
more neurons and
Well,
more.
But then the other thing is that you have A times F of BX plus C plus D. But then we wrap this whole thing in another activation function. So then instead of just continuing to compose these linear transformations, we now are introducing more and more nonlinearities.
Yep. So you basically keep transforming and then wrapping and then transform and then wrap. Yep. And I think, Dev, you were getting at the point that, there's more than one also, and that's just additive, right? So if you have more over here, that's just taking another one of these, doing transformations to it, and then adding them on top of each other.
Which is also useful because, say, for example, you wanted
Of
something
course.
multimodal, then if you add several things, you can get multiple modes.
Mm-hmm. Has everyone seen the universal approximation theorem? Yeah.
I don't think I have.
Yeah.
Oh, okay. Well, I want to show you that. Okay. So so let's see if I can sign in, because I think this one's super important. Let me go to my. Okay, I think I made one down here. Yeah, there's one. Impulse from ReLU. Okay, let's try to open this up. Open an app. So if anyone, like any of your math, it's just function approximation, right? So ReLUs can approximate any function to whatever degree of accuracy they want. So what this is I just took 2 ReLUs and I have one here. Let's see if I can get a good, yeah. So we've got one ReLU here, and then I took another ReLU down here, right? And then if you add those together, it makes this little impulse looking thing, right? Does that
Right.
make sense?
Uh-huh.
Okay, so if we add those together, we get the impulse thing. And now if I just kind of crank up the like slope on those, it
Huh.
comes up like this and it looks basically like this
square
little
wave.
impulse. What?
Yeah. Looks like a square wave.
Yes, yes,
Yeah.
okay. And so now what happens is you can imagine, like we were talking about those vertical stretches, we could stretch this however high we want, right? So let's say we're trying to approximate some function that like goes like this, right? What you would do is you take one of these and multiply it by whatever the y value is there, right? So now you can get up here. And then you would just make another one of these and try to approximate it over here. It's like basically the integral.
You can create a step function-y looking output with whatever height you want at whatever step.
Yes, thank you, Ted. Yeah. Does that make
So
sense?
like we're working backwards, like when they first taught you integration back in the day, right?
Yeah.
Yeah.
So-
Okay. That's where we're
Yeah.
going with this.
Yeah, so the theorem is that if you can make one of these, you can make any function you want.
Right.
And-
Or any distribution or whatever that you're trying to model. I think.
Yep.
Grant,
Yeah.
Grant, is there a specific theorem? I mean, you showed us kind of a numerical implementation of it, but
Yeah, it's just the universal approximation theorem.
So there are multiple ways that people have done intuition. So what Grant's showing is an intuition saying, hey, look, I can approximate any value you want over any skinny wide interval that you want. And given an infinitely wide neural network, you can compose as many of these little sticks as you want. And so therefore you could approximate any value over any domain of possible values, right? That's not
Yep.
the formal proof, but that's sort of the intuition as to why an infinitely wide neural network should have the power. Whether or not gradient descent training will ever achieve that is a separate matter, but that they are capable of
Right.
approximating any particular output function you want.
Well, they with the NTK, they also prove that how it converges to a specific value as well with the neural tangent kernel. So with NNGP, you get the function, and then with SGD, NTK, they show how it is converging towards a specific value on the last function. Is that what you're saying, Ted? NNGP is the
I don't think so. I think
wide.
this is again just exactly what Grant's showing is that if you can build this and you can make it any height and any width you want, and you can have infinitely many of those, if you just place them all side by side, you can clearly have whatever output you feel like.
And I don't know if it'll help any people, but if you've ever seen like a Fourier series, it's basically the same thing. There's a universal approximation theorem for Fourier series. It's the same thing. So yeah, so that's kind of the function transformation thing, and that's why previously, like in a previous generation of machine learning, they only had one hidden layer, right, before they started doing deep networks. And they only used one layer because the universal approximation theorem applies only with at least one layer. So they all knew that theorem, and they said, oh, all we need is one layer, right? So that was at least the theorem. But it turns out in practice, deep learning works better. So yeah, so that's that. And now sort of with that background.
By the way,
yeah.
I completely blame this universal approximation theorem
Yeah.
for AI Winter 2. The second AI winter.
So I'm glad I told everyone that. Maybe we'll go into another winter. It'll be my fault.
there's a
Okay,
new term. There's a new term on the block. It's the AI summer.
right now.
Yeah.
Yeah, I mean, it sure seems like it.
Are you being serious?
No, I
like
think that
people
was,
are saying that?
Yeah, I saw that. But that might have even been in the that letter advising us to pause. I think they referred to it that way. First time I'd heard it.
Okay, I guess it's the opposite of winter.
Yep. It's gonna be a hot one.
All right. Okay, so let's do a little more GeoGebra. So now that we've kind of got that background with the like function transformation stuff, I kind of wanted to show a couple of loss surfaces or error surfaces, whatever you want to call them. Okay, so let's open this up and take a look. And I can send you guys these links if you want them.
Yeah.
Okay, so what this is, thanks, Roger. I'll be sure to. Okay, so what this is I just made 2 data points. I'm pretty sure. What did I use? Yeah, I think I just used A and B. Okay, so I just made 2 data points, and then I made a ReLU, and then the X and the Y here are the weight space, right? So this is just a loss surface in which we're trying to get to 0 loss. So our goal is to be like right there, right? Does that, everyone with me? Yeah. Okay. And so since this is a ReLU, all this space right here, this is all flat.
Mhm.
So because ReLUs can't learn some of this area. So basically what happens is in just this dumb case of just having 2 data points, A and B here, you can ignore D. That's for something. I just did it so I could look at this transform. Kind of cool. But if we just look at A and B, we just make 2 dumb data points, and now we initialize our weight and bias somewhere. If you initialize your weight and bias here, you know, gradient descent will take you to this minimum point. If you initialize it here, you're fine. Here, anywhere is fine. But if you initialize right over here, you literally cannot learn just this simple data set with A and B.
Hey Grant,
Yeah.
for the point A, what
Yep.
are its location and what are its value?
Yeah, so the point A is like just basically I think 1, 1 or something like that. Very nearly 1, 1. And
So you're
B
saying it's a
is like 2, 2.
one-dimensional input,
Yeah.
and that's the red axis, and
Yep.
its value is the green axis?
Yep. Thanks for making that clear. Yep.
Okay.
It's just 1 dimension here and then 1 dimension there, right? And so what happens is, oh, and that's why I made D, right? So if D gets right there, it fits the points perfectly, right? And so if we turn this graph over, D should be at the minimum. So if we turn this graph over, boom, D is at that minimum, right? Because this ReLU is going straight through A and B. Okay. But now if we move D over, let's say we initialize somewhere over here, you see this ReLU underneath. Look, it's over here. If D was initialized here, no matter where you move your weight and bias, that's not affecting A and B at all. So if this is where we initialize, the ReLU literally can't figure it out.
And you have a
Because
dead
there's
neuron.
You have a dead neuron. That's right.
So can you explain me a few things here, Grant?
Yeah.
So A and B are in the data space, right?
Yep.
So your
A and
X
B
and
are the
Y are
data.
in the, but the loss surface is in the weight and bias space.
Yep. So it's a little confusing, but hey, that's the only way I can do it. Sorry. Yeah. So thank you for clarifying. Yeah. So A and B are in the data space. So this right here is like our X or our feature, and this is our target or Y, right? And then so D and the loss surface are in our weight space. It just so happens that they're the same dimensions, just so I could do it all in 3D.
Got it. So you are overloading
And then the
X and Y for
vertical, the
both.
Z, is your actual loss value.
Mm-hmm.
This height is your loss value.
Yep.
So in real life, your weights and biases will be way more number of parameters potentially than the actual dimensions of your input.
Yeah, exactly. Yep. Yeah. So this, so A and B would live on a lower dimensional space than the weight space. That's what you're saying, right, Dev?
That's right. Yes.
Yep, for sure. Okay,
And,
so I thought,
and that's only recent because we didn't used to have trillion parameter models. So, you know,
Yeah.
I don't know what's the possible values for like a 256 by 256 color image. I think many of our networks were smaller than that for a while.
Yeah.
Until now, we just do stuff with
So-
tons of compute.
Quick question. The reason that you wouldn't be able to solve that is because you're essentially, the gradient is flat out in the
Yep.
region you're talking about, right?
yeah,
Um,
and there's, oh yeah, go ahead, sorry.
Yeah, in this dead neuron space, it's all, the loss is all flat, so you can't get any sense of what direction to head.
Yep.
What happens in high dimensionality?
Yeah, so in high dimensionality, actually the same thing happens, I'm pretty sure, because you still only have those two weights and biases. But what happens, I think, in high dimensional space is you just have a ton more neurons. So a lot of them are dead, but some of them happen to be initialized just over here. So those ones start to learn.
So it's
The other
possible to
thing
still
is, if this were leaky ReLU or swish,
Mhm.
it still might never get to a good spot, because if your learning rate is small and the gradient is 0.000001, it's not 0, but it still might not be big enough to ever move you far enough to get into the interesting valley, where your loss is much better. But it would at least theoretically be moving you towards that good loss.
Right. And the point that you made, Grant, that there in Roger, to your question and the point that Grant made, in real big networks, I think no more than 5% or some very low number of neurons are actually participating. And there is some work that has happened. There's a company called Third AI, which actually takes your models, sometimes even trains your models on CPUs, because they know that majority of the times you don't need a lot of the compute power because you're not doing anything through dead neurons. So they are able to accelerate your models on CPUs by tapping onto that aspect of dead neurons, or not participating neurons, if you may.
Yeah, but are you saying they can identify? They're identifying the dead neurons and then
Yeah,
just
depending on the data and then learning the patterns during training, they are able to identify. And then so they basically do some locality sensitive hashing for the data inputs, and then based on that, they know which map it to which neurons will become active and just use those
Sure.
during the inferencing time.
Oh, okay. I see. I see what they're doing.
If you have images, if you do a forward pass on 10,000 images and this neuron never fires,
Right.
you don't need it.
Right. Yeah, just trim it out.
Yeah, and not just never
move forward.
fires, but depending on your data pattern. So if your input pattern is a cow standing facing right, then they know for this distribution, these neurons will fire based on the distribution, and they'll just pick those during inferencing. Or the other way around, if the cow is facing some other way, right, then they will have other set of neurons, and they have some heuristics to pick those neurons.
So they're actually doing it based on the input data that you're asking the model to reason about, if you will.
Yeah, during training, they identify the hash function, if you may.
Okay.
I think you're talking about a different company than the one I'm thinking of. Yeah,
Yeah,
there's another
AI.
company that's older that just does something much simpler. They just simply look to see what all your dead neurons are. They rip them out, but when you do that, you lose the regularity. Okay, so now you have a very sparse structure, so it doesn't actually run well on GPUs. So when they say, hey, we're running this on CPUs, it's not because they're trying to save you on hardware costs. It's because they can't run it on GPUs because it's now very irregular where the weights are and what they're connected to. But like you were saying, if you cut the number of weights to 1% or whatever what they used to be, then it's just far fewer calculations. And even though the CPU is slower, it accesses memory faster than GPU does. And slower,
Right.
but that many fewer calculations, you win in the end, is what they claim. I haven't used their services.
Yeah, I think there are other people doing it just because you're running on, since I work in the tiny ML space on these small platforms, people are doing something similar, maybe not quite the same, but trying to find out which, neurons, even potentially layers that we could just eliminate to shrink the model down to package it smaller.
So I'm curious that you said it was like a 5%, only 5% are active. Is it 95% are dead? Is that what you said? Dave, is he still here? He might have.
Yes, I'm sorry. I was just typing that chat message as well. So yes, maybe even lower number. To be very honest, I do not recall the exact percentage, but it is so low that they are able to optimize it by learning the hash function through hashing that, okay, for this distribution pattern, these neurons will be active, and just use that during inferencing, or even
So-
they do train also that way. But yeah, go ahead. Yeah.
Okay, so this would be true anytime I have a loss function, a nonlinearity rather, that is flat someplace, right? I get
Right.
these no gradient spots. So
Right,
I've always
like
been
ReLU.
curious. I've always been curious. Then why is it ReLU? I don't know if it's still popular or if it just has been popular, but ReLU has been very popular over time. Why is it?
It is.
So why is it if it has this problem?
I might have a couple of answers for us later.
Okay, I can wait.
And I just
Quite the
pointed out
tease.
three.
All right, Graham,
Yeah.
move us along then.
Yeah, just one last thing. So I did put it on chat, 3 companies which have optimized the neural networks on CPUs, and especially Colossal AI is very, very popular in the HPC space.
Yeah, Neural Magic was the one that I was thinking of, where they do a lot of pruning and then they run it on a CPU as a sparse network instead of a sparse matrix instead of a dense matrix.
Cool. And yeah, that's great discussion. And Roger, I do think I'll at least shed some light on what I think is going on that. And before I leave this though, because I do think this will be cool to people. Okay, so this is the ReLU, right? And one other thing I do want to point out is like, there's this minima, and this is, this is obviously non-convex, right? And it's actually not quasi-convex either. And I'm like, well, what is it? And one thing that I do think that I notice on these is it seems like if you filled it up with water, it would like all of it would pool to there's like one like uniform bottom, right? It's not like a bunch of ponds disparate. It's like there's one ocean at the bottom, right? So I don't have a name for that property, but I feel like I've seen it at least in these toy examples. In any case, so let me show you this. So this is with the ReLU. And so I'm just going to switch it to an identity function. So now we have no nonlinearity. So if I run that, of course, we just get a parabola, right? So this does not have that dead neuron problem, right? But of course, it can't fit certain data sets, right? It fits this one just fine because they're basically on a line. But you can at least see that it doesn't have that dead neuron area, right? And then I'll show us one other thing is I'll show us, I don't know whether this is the swish or the mish, but it's one of them, e to the negative x. If I show that one, looky there. So not only does it have this dead area, but it also pushes you away from the optimal location. And that's what we see with that non-monotonicity, right? So this I think is kind of cool. It's like, and I was trying to figure out why this is nice. And I had a couple wild speculations. Maybe one of them is this right here gives you energy and momentum to literally go away from it, then maybe find a different minimum over here or something, right? Because if there's a lot of minima in like a bigger problem, then there might be some minima over here, and this might push you that way if you're using some momentum. That might be one thing. Another thing would be like this bowl is deeper, right? So you've got like a deeper bowl over here. And I think I had one other idea on this. Let's see, what did I have? Yeah, actually, one thing I was kind of curious about is I thought that this might break the idea that all those bottoms like feed into the same ocean. Because if I zoom out a lot, it looks like this one goes down, but then it comes up and goes back down over here. So, and again, I think that's because of the non-monotonicity. It splits up our minima, which I think is a bad thing, but somehow don't listen to me, any thoughts or next page?
Yeah, it looks like all the rain doesn't end up in the ocean in that one.
Yeah, which is
that seems bad.
Yeah, I agree, but somehow.
So Grant, just for everyone's benefit, so when we look at this loss surface on the far right, for example, right? So that's the weights and bias initialized wherever they are, and depending depending on where the original value was, this is how the contours will look like for the loss as they go along, right?
Yep, good, well said. Yeah, so if you initialize like somewhere over here, then gradient descent will take you this way.
Right.
Right. Yeah.
Yeah, and maybe the original image that you had is even though it is looking at from towards the horizon, if you may, with some mountain on the right. Whichever way works best. Yeah. So let's say it was all the way deep behind the blue line, then it will potentially go on the left side or negative side. But if it is in front of the blue line, on the right of the blue line, then it will go towards one of those. And then it may or may not go to the actual minima, or will it?
If you're
Because it
somewhere in
depends
here, well,
on,
yeah.
well, it will always find a minima if you keep on, if you continue for many, many epochs.
This is a cool visualization, Grant. I'm thinking to myself, maybe that's why we need these really large networks, because perhaps 3/4 of the initializations fail. But that's okay because you've got, a billion weights. And so, the other quarter are just fine. And then also, I think when you composite these, then you may get into where it's not like everything to the left is just you're screwed. Maybe there's a mirror image, like you were saying, it's pushing you in that direction, but there's another a good low loss over there, and so you can stumble into different ones that work out in the long run.
Yeah, absolutely. And yeah, so I'm glad you said you like this visual, because I do love GeoGebra, and even though it seems simple and it doesn't seem as like crazy as like coding up something, I feel like we can learn a lot from it, and it's not hard to do. Like you could whip these up in no time, right? So I think that's what I like about it. And I'll just show one more thing.
Can I add one more thing, Grant,
yeah, please do.
to the question that Roger asked? So, Roger, in order to avoid falling into the trap of stuck in on that flat land, if you may, some of the things that are also applied is weight clamping. That is more on the if you go too negative, then it will clamp it to some minimum value, and it will not let you go below that value. There is this normalization also that happens. I mean, that's what batch normalization will do. So that may sometimes move your values around. Well, that is only for the data value, not for the weights, right? The normalization that we do. So maybe I take back. Yeah, but the weight
would
clamping,
normalize the gradients, though, right? Into the weights.
So weight clamping, that's right. So weight clamping and then weight decays. So that's why you have some of those where over time you decay the weight so that it's maybe getting closer to a specific range and not going too far. And there is weight normalization also to make every weight between 0 and 1. Or is it the data normalization only? Let me recall that batch normalization is only for the data, right? Not for the weights. Weights is clamping and
I think
decays.
along those lines, Dev, if you say that your inputs are normalized, so mean 0, variance 1, then I think that if you know that you're using a ReLU or whatever, then I think that tells you certain, you know what I mean? Like if your inputs can't be too big, then like what the interesting region that you want to be in for those values must lie. And I think that's why the clamping might work, because, right, if your inputs are only between, obviously, variance 1, you could have extreme outlier values, but like most of the time, right, you're right in there within, like, say, +3, -3 or something like that. So then
Right.
you know that if you're just doing a linear matrix multiply against +3 to -3, you shouldn't ever have a weight that's like -20 or something like that, right?
Right. And
Maybe?
if there's an outlier, then you have clamping and then decays over time anyway
Right,
with learning
right.
rate. Yeah.
So maybe that helps. The other thing that I'm thinking about, which does not, I don't know that it's even in the same domain as this question, but that thing that Tim Detmer saw, which is that in transformer language models, there will be outputs that get extremely large once you have a large enough model. And like he said that basically he couldn't find any threshold to say this is a reasonable maximum value and this will cover all of your activations. So if you set it to be 1,000, then nope, I found a decent percentage of activations are bigger than that. Okay, well, let me set it to 10 to the 5th. Nope, I found a decent percentage of activations that are greater than 10 to the 5th. Let me set it to 10 to the 9th. Nope. So basically, like, somehow these models have activations that are ginormous that serve some purpose, such that like they will overwhelm any residual value just by being so big that they'll, you know, overwhelm it or whatever. I don't know if that's related to this at all, but it's like it's a very surprising thing that you have all this normalization and yet still somehow you get these massive activations.
Which may be and I'm just, speculating, which may be that specific semantics gets highlighted in that particular head somewhere. You know what I'm saying? Like
Yeah.
the correlation between he and boy, right? Those two pronouns, pronoun and
Right.
noun gets correlated. And that has to be so high that it has to come out very distinctly in that layer, in that head.
Yeah. Like when I was playing around trying to give you guys toy examples, you could see that like there were things that had small bumps elsewhere, you know. But if you just had this huge thing and then did a softmax, then you just basically guarantee that you're going to get to within rounding 100% of the and anything else, right? Well, if that thing's 500, doesn't matter because I'm at 1,000,000. You know, I'm at 10 to the 5th. So it doesn't matter if you have these random other spurious values. My softmax will just crush all those to 0.
Right.
That was wild. I don't think we've talked about it, but this was Tim Detmer's when he was talking about he's been really working on 8-bit arithmetic instead of 16-bit arithmetic. And so he was trying to quantize things to 8 bits. And what he found was it didn't work. It failed. No matter what scheme he tried, it failed because he had values that were so much bigger than all the other values. They just didn't fit on a 0 to 255 scale, no matter what scale he chose. So that was like, wow.
It's pretty cool. It almost sounds like chaos theory or something. Yeah, so I think I'm gonna show one more little GeoGebra demo. And this one's kind of cool because it's gonna transition from a no activation, so like an identity function, to a ReLU, and it'll show the difference in the surface, right? So first of all, I did something a little bit different on the points on this one. I think it's easiest to see from this angle. So I made A, B, and C as points, right? So now we have 3 points instead of just 2. So the linear function, so no ReLU, no activation, it can't get these perfect, right? But since the way I drew the points, the ReLU should be able to, right? Or should at least be a lot closer. Okay, so right now, I think, let's see, what is it? Yes, it's a ReLU. So I'm gonna pull it out of the ReLU, okay? So this is just a parabola, basically, right? So it has no activation function. And so I'm gonna drag this point down, right, to about the minimum, right?
And that's
that-
probably just the centroid of those 3 points. Probably.
It's the line of best fit, right? It's the A and B you would get if you just did like a linear regression.
Okay.
Are you saying that's the same thing as a centroid or something?
I'm not sure.
Okay.
Well,
No,
the parameter space and the data space are two different. They're on one plane right now, but they would actually be two different ones, right? So it's not really centroid.
yeah. Yeah, so I think so yeah, in any case, so we've got it looking about like this, right? And so now, and you can see there's some error, right? Because if I look like that, it's not touching that 0, right? It's not touching the plane. So now we can see if I start turning on that ReLU, you can see it start to morph a little bit. And you can see that min is dropping. And it'll keep going. And eventually it'll touch 0 there, right? Because now if we move D to that, where's our min? I'm gonna make a fool of myself trying to do this live. Yeah, okay, so you can see now the min is not here, it's over here. Right, so when I turned that ReLU on, we need to move D, our parameter. Oh, I see what I'm doing wrong. Okay, there we go. Let's move to, I think about over here. Am I getting this right? What do you guys think? All right, somewhere, maybe over here. And sure enough, look, it just went through the points. It almost feels like magic sometimes. So yeah, now this ReLU is fitting through the points, and D, our, our stretch and our shift in that direction is right at the minimum of this air surface. Right? And then you can see also, look at what we have here. We have this dead neuron zone, right? All this flat area, if we would have initialized here, it wouldn't have known what to do, right? So if let's say I move D over here, we can see it's flat at this point where it can't be flat, right? So if I'm moving D, I'm having trouble because I've got a magic mouse. But yeah, so like if I move D around, this is not popping up at all. So it's not giving us, it's not making any difference.
Grant,
Go ahead, Roger. Yeah.
I was going to say, so that's assuming that you're using a gradient descent without noise, right? If you're adding noise in there, which SGD, that adds noise, right? So if the noise magnitude was large enough, it'll push that point over, not downhill, but just move it over into an area that it could then follow the gradient.
Yeah, I mean, I guess maybe I could buy that. What kind of noise does SGD put into it? Because the noise that I'm aware of is A, having a batch size that's not your whole data set, and
Right.
B, your learning rate. And in this case, let's assume the rest of the data follows this distribution more or less. That's not going to fix your problem by just picking some of them. Because
so Grant, if you said all the points did fit this, but you just happened to pick a batch that all the points were near B, or all the points were near C, or only A and C, or only A and B, then that particular batch might actually no longer be in the flat region and might shove it. It might actually have a gradient to follow.
I would still say I don't think so.
Might not.
Yeah, because the whole point of a batch is that these, so forgive me if I'm telling you something you already know, but I'm gonna say it anyway, just in case. So like, let's say all these points are along the same distribution, right? And let's say we sample some of them. The whole point of doing a smaller batch than the whole thing is to get the same error surface, but have it less computationally taxing, right? So if we only select a couple of these points instead of all of them, the whole point of doing that is that this error surface stays the same.
That is true in the long run, but what Roger is saying is accurate. In any particular small batch, you are going to get random noise, and you might get a batch that just shoves you in a very weird direction.
Yeah, I think it's possible. But even in that batch, I mean, okay, so your error surface needs to be off. It needs to be very different for that batch, right? So then you take a step in gradient descent. Now you're back to the same batch. So you have to get lucky a bunch of times, right? More or less.
Yeah, I'm not necessarily saying it'll work. I'm just saying
Yeah.
that he is right in that you are adding noise. And so then what you can show is that if you do batches, when you sum them up, they have to equal the whole data set, right?
Sure.
And so it should, on, even though you might take one, to your point, on average, you're not really going to be going in that direction. You're going to be going in whatever the true gradient direction is, right?
Mhm.
And then this is where I think for really hard problems, so like when you're learning language at the very beginning and you've just got random initialization and everything's like really garbage, I think this is where you see these big companies using huge batch sizes, you know, like 60,000 or whatever. And the reason is because small batches are noisy and it might take too long for them to average out into the direction that you want, right? Because remember, like your data set is like 1 trillion web pages or whatever, you know? And so it's going to take too long for that to average out. So then that's where they find that a mere mortal person's batch size of 2000 isn't enough. They need monster batch sizes, which gives them a more accurate, less noisy true gradient, especially early on.
Yeah, absolutely. And Roger, does that kind of, I don't know,
Yeah,
are you satisfied or?
Well, I'm actually just trying to see if this helps me visualize. I've heard before that, yeah, mini batches were originally thought of as a way of kind of computational efficiency,
Mhm.
but we actually found that the noise that they induce helps with optimization. And I'm
Yeah.
wondering if I'm looking at this and seeing, you know, I've got random initializations near that flat spot. If the noise is in the parameter space, then I can imagine it bumping us over the edge to where we can then follow gradient. And is it the case in high dimensional space? Do I end up with a lot of small flat spots or something? Is there some reason that works well?
Yeah, the other noise that I'm aware of is in the VAE space, at least in the visual, in the images distribution learning. So there they do the reparameterization of the graphical model in the central layer where there is a bottleneck. So there, so that they can do the training, they actually inject the noise from an external parameter, which is different every time, and they don't worry about it. But that's the noise injected in the network during every single training part, right there in the middle of the bottleneck layer. But a transformer, a vanilla transformer or RNN or CNN will not have that reparameterization trick.
I mean, dropout is a huge introduction of noise.
But that's awesome. Yes.
And-
yes. And that's why it helps tremendously.
And it almost always seems to help, you know, so language transformers, vision, right? They've all been trained with dropout.
And actually, so to your point, Roger, so all these are tricks to help overcome the dead neurons and also the exploding or vanishing gradients, which is related to where exactly you happen to land in your surface also. So the residual reconnection is also to help you recover, for example, right? So there are many such tricks: normalization, dropout, reparameterization, residual connections, and I'm sure there are many more that people have looked at to help circumvent this, and of course the stochastic batch size.
And even, you know, some of the vision models, when they do data augmentations, some of them are like very aggressive. Like the amount of noise they're introducing is pretty extreme. If you know, if you crop the image and you mix it with 30% a different image, and you know, like that's like a very dramatic change. And so maybe that can, really help you not get stuck.
Yeah. Yeah, or even in language models, the masked language model, MLM, right? So they are masking or corrupting. So you are injecting noise in the data. But yes, sorry, go ahead, Roger.
I was just going to say, Grant, it's really interesting and helpful to look at this from the perspective of this lost surface. So, thank you for these visualizations. Cool.
Oh yeah, absolutely. I mean, and thanks for the discussion. Yeah, I agree. The randomization is probably, I mean, it's key, right? Yeah, and so we have like 10 minutes left. What should I kind of speed through the rest?
Oh, I don't know how much you have. Please keep going.
Okay. So I mean, there's definitely some stuff left. Okay. All right. So this part is a little on activation
Hey,
functions.
Grant, before you go too
Yeah.
far in this, how much stuff is left? What are we talking about? Are we talking another session or?
I mean, it's up to you guys if this is interesting, or I mean, because there's this little chunk here on these activation functions, and then there's definitely some stuff we could do on optimization. But I think you had something planned, so I can do whatever people want.
Yeah, I guess that's it. I mean, my stuff is just a paper read, so we can shift it back. It's not a big deal. So I guess I'll throw it out to the crowd, if you will, wisdom of the crowd here.
I'd kind of suggest or throw out there that this idea of, I think going back to these core fundamentals is really interesting and helpful. On the other hand, I don't want to span, forever on those. So I wonder if we could kind of mix it up where we can queue up some of these core fundamentals, do some more of the language model stuff, and then cycle back and forth between these over time.
So may I throw my suggestion, Roger? So I'm thinking that given that Grant has created all this presentation, and which is super helpful and engaging, if we assume this can be done by next week, I like your suggestion. We should keep doing that going forward, but maybe he can finish this up next week. 5 minutes or 10 minutes will not be doing justice to these two topics of activation functions and optimizations for sure. But if you think, Roger, that one session will not be enough to complete the rest of those topics, or maybe Grant has more, then sure, we can interleave more aggressively. That's just my suggestion.
Yeah, I'm kind of with you, Dave, on that. Just because we're kind of moving a direction, and if we go somewhere else, then we have to come back, and then there's a cycle time or whatever to do that. So, Grant, is this a good breaking point then if we were to go to another session?
Yeah, I think so. I could show that Curse of Dimensionality thing that I sort of had on the back burner just for the next 10 minutes if you want.
Okay.
And
yeah.
then
Yeah, if you want to do that, that's fine.
Did you have something else in mind?
No, I just wanted to get this point about where we're going, next week and that sort of thing out before we kind of headed there, and you tried to like ram this down. It felt like we were going to have to ram a lot in 10 or 15 minutes. So that's all I was concerned with.
Yeah.
Right. So then the official plan is Grant or Jerry next week?
I think Grant, it makes sense just to, if there's more, if you think you can finish up next week, do you think that would be reasonable?
Yeah, I'd love to.
Okay.
All right, cool. So Grant next, Jerry in 2.
Sweet. That sounds good. All right. And some people let me know if I'm hogging, so I don't want to do that. All right. So let me go find that Curse of Dimensionality thing that I was gonna. Yes. Okay, here we go. Notice that I'm hiding all the slides from you. I don't want you to see the things that are coming. Okay, so this is something I had actually experienced it, and then I kind of like tinkered with it. And then just the other day, I found a YouTube video on it. So it was kind of a cool experience for me. But so, oh goodness, no. All right, I'll just, oh, I think it's because I'm not signed in. It's a little anticlimactic. There we go. Come on. All right. Okay, so this is a little bit on the Curse of Dimensionality, and I noticed it when I was looking at some stock data, but I'll kind of just go through like the logic of it. So basically what happens is in this picture here, this person had talked about it in terms of like nearest neighbor approaches. And so like if here's your data point and you're trying to do a nearest neighbor thing, you know, what is the worst case scenario that could happen is everything is pretty far away, but they're all like sort of equally far away, maybe, right? So it's like, there's no reason to pick any of these neighbors in particular. And none of them are particularly good because they're not close, right? So this is sort of like a pathological case for nearest neighbor, right? And so I saw that this is basically exactly what I had noticed. So what I was trying to do was a nearest neighbor on stock data, right? So I had like 50 or 500, I can't remember how many stocks, right? And so I was looking at the returns, like daily returns on all those stocks. So I was looking at either 50 or 500 dimensional space, and I was finding that there were no near neighbors. And I was like, what is going on, right? And so this is what I did, okay? So this example is in 6 dimensions, just to kind of give a flavor. And so what I did was I generated on a uniform distribution, just a uniform distribution, so they're all equally spaced in those 6 dimensions. And then I just chopped out the corners, so I had a 6-dimensional sphere, right? And you can see sort of the distribution here. And then what I did was I plotted, I picked a point and then found all the distances between them, which is the same thing as taking any two, finding the random distance between them. And here are all the distances. And remember, this came from a uniform distribution, right? So these should be uniform right here, like flat.
Yeah, you should just be a straight horizontal line, right?
But it's not. This is actually the behavior that happens, and this is what should happen actually. Because this is the same thing as what this video is showing, right? So from any given point, nothing is close, and then all of a sudden they start popping up far away. That is exactly this. Pick a point, nothing is close, everything is far away. And the reason that's happening is because the points have like an equal like density and like volumetric space. The volumes are growing at a rate to the 6th, right? So this shape right here is actually, this is to the 5th because it goes proportionally to the surface area, right? So, and if we were looking at a 3-dimensional space, this would be growing at a squared, right? So I plotted this against a 5th, and it matches almost exactly, right? So this plot here is this plot, okay? And now what this one is I like normalized it by the volume, and sure enough, it's totally normal or uniform. So if you want to do this like distance thing, you could look at it from a volumetric distance perspective, right? And that's how you pull out that uniform distribution. Kind of cool.
Definitely.
Nice.
Definitely cool.
So
Yeah.
obviously, if you had 50 stocks or 500, it's that much dramatically worse.
Oh,
than
yeah.
6
Right.
dimensions.
Yeah. And that's what I was doing. I was like trying to do a nearest neighbor, and there was like one like weird one, and then everything else was a million miles away. And I was like,
Yeah.
well, even if, even that near one isn't even near, right? Yeah.
Yep. So that's why people use cosine similarity in their searches.
Mm-hmm.
There's another thing that I saw. I'm trying to remember, where did I see it? It was a book we were reading in, I think, the San Diego meetup, but I can't now remember what it was. But basically, when you look at these image generation models, oftentimes they will talk about, we start with an image that's just Gaussian noise, right? And so imagine that you have pixel values where 0 is black and 1 is white, okay? And so you do a Gaussian distribution with mean of 0.5, okay? So 0.5 is a medium 50% gray, Okay. So if I asked you, if I just picked like one pixel at a time, you and said to you, what do you think like most of the pixels are going to look like? You would probably say they're probably pretty close to 50% gray, right? If I just said draw one pixel out of a Gaussian and have it be a black and white pixel and just have the intensity mean 0.5, whatever, right? And you're like, yeah, and sometimes, you know, you'll get dark ones, sometimes you'll get light ones, but that's absolutely true in small numbers of dimensions. But you have a whatever 256 by 256 image and it's actually color, so then you have, you know, 256 times 256 times 3 different Gaussians you're drawing. And in that high level of dimensionality, in fact, and I can't quite wrap my head around it, I've seen the math, but because of this whole business of like distance, you know, being this square root measure, but as you're saying, volumetrically, things grow to the whatever n-1 power, you know, what ends up happening is all the density of points are not actually near the middle, they're actually in a donut around the middle. So in other words, you were doing the distance from an arbitrary point. If you do the distance from the origin, the center, the mean of all the things, you get the exact same effect where all the points are almost uniformly this far away. And so the point that's at the middle would be 50% gray, where you get like a half value of blue, a half value of yellow, a half value, blue, green, red, whatever, on all the pixels. So if you actually got something near the mean, it would just be this almost uniform medium gray picture. But as we all know, when you say, give me a draw from a random Gaussian distribution, it never looks like that. It looks snowy. And so I had never really thought about it until something I read. They were talking about this curse of dimensionality. They say, no, everything doesn't live near the middle. Yes, in 1 dimensions or 2 dimensions, you see this nice bell shape and everything's, you know, towards the middle. But when you get to higher dimensions, it's actually all in this whatever n-2 dimensional donut annulus around away from the middle. And so then in that donut, basically you have some extremely large blue values and extremely small yellow values, and it looks like snow with these bright and dark varying pixels. But it never occurred to me like to even think about like, oh yeah, that's right. Why is Gaussian noise not look gray? It actually looks very colorful.
Yeah, because Ted, if you think about it, I mean, if you focus only on one dimension, yes, it's normal. But when you add another dimension, so if you marginalize along that one, you will get that normal back. But if you look at it jointly, then you have reduced your mean space, right? But the distributions space that you select sample from has increased. And then as you keep on going more and more dimensions, the intersection will be that thin sliver, which is the donut will become thinner and thinner and thinner. It will basically become like in 2-dimensional, just like a circle.
Yeah.
You keep on adding more and more dimensions.
So to get a all gray picture, you'd have to just be extremely lucky where every one of your thousands of draws gave you a number super close to the mean, and the odds of thousands of draws all being super close, it's just almost never going to happen.
So there is a very,
oh wow, that's crazy.
Yeah, there's a very good implementation from Facebook called Facebook AI semantic similarity, which basically takes these high-dimensional data points and tries to find the similarities between them, which is finding which one is close, right? So one thing to look at, Grant, would be that library if you have not already looked at it. So that does approximate nearest neighbor implementation by doing quantization for pieces of the dimensions at a time and putting them in again, hashing buckets, and then trying to figure out, okay, for each of these hashing buckets, these points are close, and then applying that at a higher level in a hierarchical manner.
and I'm sure it's a complete coincidence that the Facebook whatever search, the acronym FAISS happens to be pronounced face.
Yeah, AI semantic similarity. Yeah, so that can
Yeah,
scale to
a
billions and
pure
billions.
coincidence that AI semantic similarity happens to sound
Yeah.
like
And-
face.
And
But of
they
course, you know,
provide-
they changed, now they're meta AI research. So
it's Mace now.
I don't know, but face no longer makes sense because
Yeah.
Okay.
All right, well,
very cool
we
stuff,
re-
Grant.
thanks. Thanks for all the talk.
I once saw another notebook where I don't remember exactly what they did, but basically they just like did uniform random numbers like one-dimensionally and then actually computed whatever some, you know, and then they just like did a loop where it's like 2, 3, 4, 5, 6, 7, 8, 9, 10, and things look pretty good up till I don't remember, you know, like 5, 6, somewhere around there, you know, and then things really just go completely to, you know what, like somewhere around 10, 12 or whatever, where you're like, what? Just garbage.
Mhm.
And that's not even that high dimensionality, right? That's not like millions, thousands, whatever.
Yeah, the other thing to people bring the example for high dimension is the comparison of sphere, hypersphere, and a hyper cuboid or whatever it will be called, and how the sphere in higher dimensions, and I do not recall all the details of that, but it looks really pointy. It doesn't look like sphere at all. Or yeah, I mean, if you want to read about that, you know, that would be an interesting read as well. What happens to if you look at the rectangle with radius, sorry, a circle with radius r, and a rectangle with equal to 2r diameter, the rectangle will, the circle will be entirely inside the rectangle, but as you keep going higher dimensions, things start to change. So, and how that happens, I do not recall, but I've read very interesting thing about it, and if I can find it, I'll definitely share that.
Yeah. Yeah, it's like, how can a hypersphere of radius 1 be outside of a cube, hypercube of side length 2? Like, it seems like that just shouldn't work because, you know, a circle is inside of a square and a sphere is inside of a cube. But once you go to high dimensions because of this whole thing, then the hypersphere actually sticks out from the hypercube. And eventually
And it's
more
just
and more
pointy.
and more density to the point where almost all of the density is outside of the hypercube, which is like, what the?
Yeah. Should we wrap up this week then and plan next week, Grant, continuing?
That works
Sounds
great for
good.
me.